When is this lecture ending? It's ending in 15 minutes. I don't know. 15 minutes. Okay, I covered way less in this lecture than I intended to. Okay, so the next topic I want to move on to is orbital dynamics. So rather than immediately going in and trying to solve the Einstein equation with this point particle source, I'm going to describe some general properties of the orbits we're looking at. So for the moment, just assume that the orbit satisfies an equation of the form I've written down previously. The covariant acceleration is epsilon f1 plus epsilon squared f2. And for the moment, don't worry about what these are. I will get into that in detail later. But we just have some self-forces on the right-hand side for now. So at leading order, we have the geodesic equation. So at leading order, the motion of the particle is a geodesic around the big black hole. So the first thing I want to do is just discuss properties of geodesics without worrying about the fact that the actual motion is accelerated. Have all of you studied geodesic orbits in Schwarzschild? No? How many of you have not studied geodesic orbits in Schwarzschild? Quite a small... The first question was, have you studied? And since no one answered that, I asked, have you not studied? So it looks like most of you have studied geodesic orbits in Schwarzschild. Geodesic orbits in Schwarzschild spacetime. So geodesic orbits around a Schwarzschild black hole. And yes, almost everybody has studied it. Okay. So I will just very, very quickly remind you of their properties. So the metric of Schwarzschild is minus f dt squared, where this f is 1 minus 2m over r plus f inverse dr squared plus the metric on the sphere. We have a time-like killing vector, zt, alpha, which is just a component in the t direction. And for each killing vector, we have an associated conserved quantity along geodesics. So this gives us the orbital energy, E, which is minus U alpha contracted into ZT. That's a constant of motion. Then we have see alpha phi, the azimuthal killing vector, which is just Kronecker delta in the phi direction. And that killing vector tells us that the z component of the angular momentum, which is u alpha contracted into z phi, is constant. The other two killing vectors correspond to rotations about the x-axis and the y-axis, and so they correspond to conserved angular momentum in the x direction and conserved angular momentum in the y direction. So Lx, I are also constants of motion. So when you take these lists of constants of motion, well, the first thing you can do is just set these to be 0, and that just corresponds to choosing a preferred equatorial plane. So because all three components are constant, you can always just choose your orbit to be within the xy plane. And then when you look at the geodesic equations, you find that r dot squared is e squared minus f times 1 plus Lz squared over r squared. So this gets called the effective potential. It's just a function of r. And we're going to be looking at bound geodesics, so ones that don't escape out back to infinity. So in those cases, we have two turning points where our dot squared is equal to 0, which means e squared is equal to v of r. So we have two turning points on the orbit, and we can parameterize the orbit using Keplerian type parameters. The eccentricity, E, which is r max, the maximum radius of the orbit, minus r min over r max plus r min. So that's the same definition you would use just for Keplerian orbit in Newtonian physics. And something called the semilattice rectum, which is 2 times r min times r max over total mass, or sorry, the mass of the big black hole with r min plus r max in the denominator. So this total, this capital M, the mass of the big black hole, is just put in there to make this dimensionless. So in terms of these parameters, we have that the minimum radius of the orbit is Pm over 1 plus E, and the maximum is Pm over 1 minus E. And note that from this expression, E has to be between 0 and 1. Yeah. P. So P is the semi-lattice rectum. I don't know Latin, so I don't know why it's called that. But I will draw in a picture what these mean on a just the ellipse in a second. So we can find relationships between P and E and capital E and Lz by solving this equation at R max and R min. So we solve E squared equals V of R max and E squared equals V of R min to find expressions for the orbital energy in terms of these two parameters P and E, and the angular momentum of the orbit in terms of those two parameters. So specifying P and E is equivalent to specifying the energy and angular momentum of the geodesic. Now, we can go one step further towards how things are done in Keplerian orbits by writing the radius of the orbit as a function of a radial phase in this form. So when psi is 0, we have Pm over 1 plus E, which is the minimum orbital radius. And then when psi is pi, we have the maximum orbital radius. So this function just oscillates between the minimum and maximum smoothly. So if psi was equal to phi, the azimuthal angle on the orbit, we'd have an ellipse. So here's where I'll draw what P means on an ellipse. So this, remember, is the semi-major axis, which is labeled with an A usually. This is one of the foci of the ellipse, and this distance here is the semi-major axis times the eccentricity. And then this distance here, so orthogonal line up to the orbit, that's what P is. So you could work with A and E, or you can work with P and E. For some reason, for relativistic orbits, people always use P. I don't know why nobody uses A. Okay, but we don't have this. Psi here is not equal to phi. We can write down the relationship between them, d phi d psi is d phi d tau times d tau dr, just using chain rule, times dr d psi. And so d phi d tau we can write in terms of Lz. This is just phi dot. Phi dot is Lz over r squared. D tau dr is 1 over r dot, and we've got r dot written here in terms of E and L. And we can just explicitly write down what dr d psi is just by taking the derivative of this with respect to psi. So if you simplify all of that, what you get is an expression that's the square root of p over p minus 6 minus 2 e cos psi. So this is clearly not equal to 1, which we would need in order for psi to be equal to phi. And in fact, this is strictly larger than 1. So what that means is, if psi goes to psi plus 2 pi, so you're going around 1 radial cycle, so from the max into the minimum, back to the maximum, then phi increases by more than 2 pi, because the rate of change of phi with psi is bigger than 1. So typically, what you have is a precessing ellipse. So we don't have an ellipse like that. We have an ellipse that's precessing with time. So say something like this. Or we can have an extreme case, which are called zoom whirl orbits. So in that case, we come in and we zoom and whirl and whirl and whirl and whirl. We come back out sometime. We keep on whirling, come back out sometime, and like that. And by choosing P and E appropriately, you can make it whirl as many times as you like, infinite number of times if you want to. So here, we have r as a function of psi, and phi as a function of psi. Last thing we need is t as a function of psi. So how does the actual Schwarzschild time relate to this parameter psi that we've introduced? And we can find that by, again, just using chain rule. dt d psi is dt d tau. So dt d tau is, I'll call t dot, which is E over f of r. And then d tau dr dr d psi, same way as we did over there. So we can write that as just t dot of r of psi over r dot of psi times dr by d psi. And so this is some function of psi. You can then solve to get t as a function of psi. Okay, so I'm going to end there and go to Kerr geodesics tomorrow. Thanks.
Thank you, Adam. So now we plan to have an extended discussion session. So you can ask questions related, of course, to the last lecture, but also, I mean, more broad questions about your life and gravitational waves in general. So this psi has a name?
Probably.
Okay.
I would just call it the radial phase.
Okay, I'll look it up if it is. The real
anomaly. There is a real anomaly, which is psi. The eccentric anomaly. I don't know if you use it, Adam. And the mean anomaly, which is just proportional to time. You know.
This psi is the real anomaly. Okay. So there are basically different ways to parameterize the angle in the orbit. So phi is the real angle.
Yeah, so phi is the actual angle of the orbit in the plane of Schwarzschild. And then psi tells you how far you've progressed along this oscillation between minimum and maximum radius. And in a Keplerian orbit, phi would equal psi up to a constant.
Okay.
So only in the Newtonian case we have phi equal to psi, or is there any physical situation in general relativity that we get an ellipsis?
So I mean, generically, we have orbital precession in relativistic orbits. Luke would probably be able to suggest something.
I think that there are so in Newtonian orbits, for Newtonian orbits, the orbits are closed. You know, they come back to the same position and so on. And there are only, so it corresponds to the Newtonian potential, which is 1/r, the Newtonian potential. And there are only two potentials which admit closed orbits, which is the Newtonian potential and the harmonic potential.
Yeah, what, sorry?
Harmonic potential, that is a potential r square instead of 1/r. Omega square, r square, if you like. The harmonic. All the other potential yield to unclosed orbit, for instance, precessing orbits.
So on the subject of closed versus open orbits, let me actually say one thing about that. So for this orbit, or for these classes of orbits in Schwarzschild, the motion has two frequencies. So a radial one, let me write it as two periods. A radial period corresponding to the travel time from maximum to minimum back to maximum. And the azimuthal period, which is the average time it takes to go around from 0 to 2 pi actually in the plane of Schwarzschild. And on the closed versus open, in general, because you have these two periods, the orbits are not closed. So those orbits that I drew over here, it'll never return exactly to this point and keep repeating itself. So orbits are not closed. But if nr tr is equal to n phi t phi for integer, positive integer nr and n phi, then you do have closed orbits. So for these special cases, so for example, if t phi is equal to 2 tr, then the orbit looks like that. So for these special cases that are called resonant cases, then the orbits are closed. So this does two azimuthal orbits, or two azimuthal periods for one radial period. Yeah, if this relationship holds, then you'll have some number of radial oscillations. We'll give you some number of azimuthal oscillations, and you'll get back to where you started. So this is less relevant for Schwarzschild, but these resonant type orbits will be more important for Kerr.
Sorry, T phi, can you say again how it is defined?
T phi, the average of this integrated over a period, so over one oscillation. So it's the what's that? Sorry.
Yes.
Yeah. So this is the azimuthal frequency, and T phi is 2 pi over that.
Okay.
So why is important to study the geodesic orbits in Schwarzschild, for example? I didn't see the approximation, the perturbation theory.
I guess I erased it. So the general equation of motion was epsilon f1 alpha plus higher order things. So at leading order, this is just 0, it's just the geodesic equation. And so at leading order, we can treat the orbit of the particle as a geodesic in the background spacetime. And the physical background spacetime will be Kerr, not Schwarzschild, but I'm just discussing Schwarzschild as a stepping stone to get to Kerr.
Okay.
And then after that, I will discuss how the actual evolving orbit plays into things once you're not approximating it as a geodesic.
F1 is the self-force.
This is the first order self-force. There will also be a spin term
And
in there.
this contribution, this is in general is local or non-local?
It's known or unknown?
Yeah.
It's known, yes.
Is it depend on a gauge?
It does, yes. Yeah.
I will wake up because I'd like to get some questions from the audience. Please.
Yeah, sure. Absolutely.
If there are some questions to my lectures.
Yeah. So this is general discussion section about the third day and gravity.
Oof.
I have a last question for Alan. How different is the theory of self-force of particles to the self-force in electromagnetic field? In the electromagnetic case, you can also compute the self-force. Is it very different? You have I don't know if they differ in a
So
qualitative.
the electromagnetic self-force in curved space-time is very, very similar to the first-order gravitational self-force.
Yeah, maybe you can anticipate some more. The curiosity is
The small parameter would be the charge of the particle divided by the mass of the black hole.
I think it's charge squared, maybe
Charge squared,
something.
yeah.
Yeah. So I don't know how much you know about the electromagnetic self-force in curved space. Anything? So in flat space, it's just the Abraham Lorentz Dirac force. Actually, yeah, and I can use this as an opportunity to discuss something that I wasn't going to put in the lectures, but just because I didn't think I'd have time for it. So the ALD equation, Abraham Lorentz Dirac equation, for an accelerating charge in flat space has the form a dot, let me write it as external force, time derivative of the external force. So that's like you apply an external electromagnetic field, it accelerates the particle, and that acceleration creates an electromagnetic self-force that affects the motion.
why the time derivative?
This is the time derivative of the external force, so oftentimes this will be written as like the third derivative of the orbit, or of the trajectory, but then your equation is third order in time, and
So how do you compensate the dimensions?
oh, I'm just being super sloppy, not paying attention to dimensions.
Yeah, but what is the scale?
So I think you have q squared over m. I don't remember what else plays into it. I think this is the only thing. Yeah. So, but the only thing I wanted to stress about this is that the self-force is just due to the fact that your particle is accelerating. So that's electromagnetism in flat space. In curved space, you have an equation called the DeWitt-Bream equation. And here you have an explicit Ricci term. Again, I'm not paying attention to factors. I don't remember what the factors are. Plus, again, something that's like external field dotted. But then you also have another term the tail term, which is an integral over the entire past history up to the current instant. And in here you have the Green's function for the curved space Maxwell equation. In the uncoupled case, it's like this. You have a Green's function for this box operator, and in here you have u beta, an integral over time, and there's probably a q hanging around. And what this is a consequence of the fact that in curved space, electromagnetic waves get scattered off of curvature. They don't follow just null geodesics of the space-time. So if you have an orbit like this, so say this is gamma, and you want to calculate the force, the self-force there, this is actually an integral over the entire past history up to that point. So an integral over all of this, and that's coming from the fact that down here, you emit electromagnetic waves, but they get scattered back and intersect the particle up there. And then the story for linearized gravity is essentially exactly the same. This doesn't work very well. Yeah, so for linearized gravity in the Lorentz gauge, you have the same picture. And it was derived by Mino, Sasaki, Tanaka, Quinn, and Wald. So this is the first order equation of motion in the Lorentz gauge, and it again has the form of this tail integral. How do the indices work on this? Too many indices. I don't remember what indices work here. So this is not the form of the equation that's typically used in modern calculations, but it's the same kind of idea where here you have the linearized gravitational field propagating out, being scattered back, and interacting with the point mass at this point. I really should remember the Misataka equation. Do you remember? I don't think there should be that many U's. Actually, wait, no, it's significantly more complicated than this. Yeah, that's the problem. It's something like this, gradient of Green's function. And the indices are messed up. They're not quite these indices, but physically it's the same picture. And yeah, there should be a derivative here somewhere as well, because the force is a derivative of this backscattered radiation, roughly speaking. So that's a very long answer to your question, but hopefully it's informative.
Next question?
Yep.
No, my question is on the you have the derivative of external force.
Yeah.
Quindi in some sense, for resolve the equation, is necessary 3 initial conditions, because you have in general in classic physics for resolve the equation of motion, we give the condition on the mass on the position velocity. But if you have the derivative of acceleration, is necessary another condition.
So it depends how you derive this equation. If you take the point particle too seriously and you say I have an exact point particle, then this comes out to be a derivative of the acceleration. And then this is not a well-posed thing. But if instead you consider some asymptotically small charge distribution, and you're looking at the limit as it goes towards zero size and charge and mass, all going towards zero, then really what you do get here is the time derivative of the external force, not the time derivative of the particle's acceleration. And then it's an ordinary second-order differential equation.
We will discuss the problem of the regularization as well later.
Yes.
For instance, is there a mass renormalization which is necessary? And so
No,
on?
there's no mass renormalization.
Yeah. But you will explain why.
So
because
what I'll be covering is all matched asymptotic expansions, and then nothing gets renormalized, nothing's ever infinite.
in all the papers about gravitational cell forces, I remember that there was a mass renormalization, which apparently has disappeared now.
So that appeared in the Mino, Sasaki, Tanaka paper, the very first paper that derived the first order gravitational cell force. And they had two derivations in that paper. One was based on matched asymptotic expansions, and that's what I'll be covering later in the week. The other was based on energy conservation in a small tube surrounding the particle. And there they actually had various infinite quantities that they just discarded without any justification. And they also had a correction appearing to the mass of the particle. But I don't know how to interpret their correction. There's a different quantity that is kind of like a correction to the mass, but it's pure gauge, so it's not actually a real physical correction to the mass that appears in the Lorentz gauge at the second order perturbation. It does not agree with what they had from this calculation, but essentially this calculation, no one ever did any more with it because they were just throwing away infinite things without any justification. And so they were really using the matched asymptotic expansions as a better way of doing the calculation.
Is it possible to discriminate dark energy models with gravitational waves?
Is it possible to discriminate which?
Dark energy models or modify theories of gravity with gravitational waves?
Certainly. So when I said earlier that MREs would allow us to test GR with great precision, yeah, you're looking for deviations from GR, from modified gravity effects. So you can look at very broad deviations, like some theories will have dipole radiation, which is obviously totally different from GR. And you can have things like objects without an event horizon, so then the signal would not cut off when the small object plunges into the black hole. You just have a signal that keeps on going. So these are very general kind of qualitative things you can measure. But then also, when I say you can measure the quadrupole moment of the big black hole and see if it agrees with the Kerr quadrupole moment. So the deviations from the Kerr quadrupole moment would be modified gravity effects or string theoretical effects. So actually putting that into the model that I'll be describing can be tricky because we need to go to second order in perturbation theory, So let's say you have a background plus a pure GR first order correction plus a second order pure GR correction. So these are the perturbations that I'm talking about. And then let's say in your modified gravity theory, you have some other small quantity, some coupling constant or something, times a non-GR metric perturbation, and potentially higher order in lambdas. Well, then because it's a nonlinear theory, you'll have this lambda coupling to this epsilon, and you'll have things that are lambda times epsilon, and it's a complicated mix of things. So in order for us to be able to accurately model these types of things, what we really want is that, or we have to kind of restrict ourselves to lambda being, well, now much, much smaller than epsilon. So we need whatever coefficient is coming in front of the non-GR perturbation has to be much, much smaller than the mass ratio, because otherwise we'll have to deal with complicated coupling. If it's much, much smaller, then we can just add this linear perturbation on top of what we have from pure GR, and it's not too much trouble.
I think that your question was also, is it possible to discriminate models for dark energy? That is, models where you have a field which plays the role of the cosmological constant, and therefore which is responsible for the acceleration of the expansion of the universe. Is it possible to discriminate these models with gravitational waves, which has been indeed the case last year with the binary neutron star event, where it has been checked that the velocity of gravitational waves is 1, is the speed of light to within 10 to the minus 15. And this invalidates, or this rules out alternative theory for dark energy. Notably, there is a very general class of scalar tensor theories which were motivated by the dark energy, which have been ruled out by this observation of gravitational waves.
I wanted to add the answer to this question because this is a very active field of research. So, in addition to what has been said, can I answer here?
Yeah.
There is basically the main application of gravitational waves at the moment to cosmology. Maybe after this school you can come up with a new one. But so far, the basic application is that basically we have an observatory, and then there is a coalescing binary here happening. So we see the gravitational wave. What happens is that the gravitational waves, as you will see tomorrow or the day after, are very well predicted. So their amplitude is very well predicted in terms of the actual phasing of the waveform. So the phasing of the waveform will be qualitatively the same, but quantitatively will depend crucially on the parameter. So by measure the intensity of the wave that reaches here, and by measure the intrinsic parameter of the source through the phasing, to how this oscillation change in time, one has both an apparent luminosity measure and then an intrinsic luminosity measure, okay? So because the apparent luminosity, well, you just measure the amplitude that reaches your observatory. The intrinsic luminosity is measured through general relativity by the imprint the general relativity puts into the phasing. So this is something quite technical, but you will see in the rest of the week. So, and you can already imagine, if you measure both apparent and intrinsic luminosity, you can measure the distance, okay? So this is crucial. You have the distance, and then you have the Hubble relationship. Okay, now I don't remember here, but there is a factor. I mean, the Hubble relationship is just the first order in an infinite order relationship between redshift and the luminosity distance. So this one you measure purely gravitationally. If you can measure the redshift with some other way, you have a gravitational measure of H0, which is completely independent from other measures, from standard candles, from cosmological probes. So this is the main application so far of gravitational waves to general relativity, to have cosmological inputs through general relativity. Basically, go and measure. I mean, for the moment, the distances we see one event at z.01. So forget measuring this. But okay, we saw one event, and that was a binary neutron star merger for which we measured the luminosity distance. And the redshift was measured because it was identified the hosting galaxy. And of course, once you see that the object was in that galaxy, measuring the redshift of a galaxy is very easy, because the galaxy is always there. There are a lot of lines, you know, they should be there. So now the point is that in the future, so now we have basically one point, which has negligible error in redshift and somehow a big error in luminosity distance. Because yes, we do measure this gravitationally, but with some error, of course, which for the moment is 10, 15%. So the idea is that to populate this graph, of course, this is a wild dream. I mean, for the moment, we just have one point. But in my wild dreams, when, you know, at night, I can dream whatever I want. So I populate this graph with thousands of these measures. And basically, this is the work of my master student. I mean, to populate this graph with thousands of measures. And then you will see what is the best fit. And then you can measure these, I mean, all the orders you want, I mean, if you have enough points. And then other thing, and so this will tell you, I mean, how the dark energy actually behaves at large redshift. You can also learn a lot of stuff about the distribution of galaxies, for instance, by looking at how these objects are distributed in Z. So for the moment, we have one object as Z equal to 0.01. But maybe in the future, we see really a population of these objects in redshift. And we see that they are peaked at redshift 1, 2, I mean, we'll see. And then we understand how how basically the transition from star formation to merger formation, because star formation we more or less know, we have good guesses of the distribution of star formation. And then with gravitational wave we see merger formation. And then once we measure 1,000 of these objects, then we'll see if the merger formation is a distribution which is displaced or overlaps with the star formation. And then we learn about evolution of stars and so on. Sorry, but wait, something I forgot to mention. Here we have one point of which we know the redshift with basically 0 error, and we know the luminosity distance. But suppose we didn't see the gamma ray burst, we didn't see the transient, the kilonova, joined with this merger. No? We saw this merger, we saw the optical counterpart, and we say, it comes from the galaxy. Suppose we didn't see any electromagnetic counterpart. So we would have been missing this Z measure. But gravitational waves, since they are measured by different observers in different locations, the gravitational wave arrives slightly earlier to one detector and slightly later to the other detector. So we can actually pinpoint the region in the sky where the gravitational wave was originated, just because of the delay among the detectors. And so we say, okay, suppose we didn't see the counterpart, but we know it came from this region in the sky, which is 10 degrees square, 15 degrees square. Then we can go and look at galaxy catalogs and just take all the galaxies which are there. And then we say we have 100 galaxies, fine. So the points would have been something like this, okay? Because we have to put here, sorry. The error in the distance is the same, because we measure gravitationally. It's just the error in Z, which becomes very large, because you have to allow all the galaxies there. Okay, you do it once, you learn basically nothing, because you have a huge error on Z, so basically any curve goes through there. But suppose you have 100 detections. So you have large error on luminosity distance, and a huge error on Z, just because you are taking the galaxy which is the right one, and 99 galaxies which are not the right one. But suppose you can do this for many, many detections, all with a large error in Z, and a reasonably small error in D. You pile up all of these. Okay, maybe you don't get good information on this higher coefficient of the luminosity redshift relationship, but the Hubble constant, it has been simulated, you can measure to 5% with 100 detections. So 100 detections without counterpart, so without measuring Z, but just taking the Z of all the galaxies which are in your error box, you get H0 measured to 5%. this is not science fiction because it's already being done with the few data we have. Now we have 5 binary black, 6 binary black, no, 5 binary black holes plus 1 double neutron star. You can already do the game, play this game, and you get an H0 measure, which is very poor, but it shows that it can work. And piling up 100 of detection, then you can have a H0 measure, even without counterparts, just by counting the galaxies. Why this is good? Because when we talk about redshift of 0.01, black holes have been seen up to redshift 0.2, galaxy catalogs are complete, basically. All the galaxies which are there up to 0.2, we know. If you start going farther than that, then galaxy catalogs have holes.
Just to add to what you say, first of all, there has been a recent resolution of the International Astronomical Union to rename the Hubble constant the Hubble-Lemaitre constant. So now the Hubble law should be called the Hubble-Lemaitre law, which I think is completely normal because Lemaitre published actually this law 2 years before Hubble, but he was not recognized because he wrote it in French and he didn't allow an English translation. And so now that resolution that has been voted at, I think that 78% of people voted for this resolution. Okay.
So
But
remember this when you write papers. If they end up on Blanchet's desk, then it will be rejected.
Probably, yes. Okay, but just to, yes, regarding the measurement of the Hubble constant by means of gravitational waves, this is extremely interesting because, as you said, it does not depend on the usual standard candles of usual astronomy, you know, to use supernovae explosion, to know the distance, because we expect that we know the total luminosity of the supernovae, and so on. And so gravitational waves is a completely different method, and this is very interesting and important because for the moment there is a discrepancy between two types of measurement of the Hubble-Lemaitre law. There is a traditional measurement using the supernovae. So we think that some supernovae, we know the absolute luminosity by the curve the luminosity curve that they have, and so from the apparent luminosity we know their distance, and we can measure the Hubble parameter by that means just with supernovae. Okay. And on the other hand, there is a measurement from the cosmic microwave background, the CMB, and it is a global fit of a model to fit within the lambda cold dark matter model for cosmology, the standard model of cosmology, which is fitted with all its parameters to obtain the spectrum of anisotropies of the CMB. And among these parameters, there is a H0, the local value of the Hubble-Lemaitre parameter, and there it happens to have a small disagreement for the moment. So
67, 71.
Exactly.
Kilometer per second.
Yeah. Yeah. And so we expect that in coming years, quite soon actually, gravitational wave will be able to distinguish between these two measurements.
The gravitational wave measurement of the Hubble-Lemaitre constant through the electromagnetic counterpart gave this PDF. Basically, it's so wide that it encompasses both values. The idea is that piling up tens of detection, maybe this will shrink to value here or there. But actually, it doesn't use the standard candles. The local measurement of H0 through it's usually says standard candle, but it's only through the Cepheids.
Because there are two calibrations. I think that first the Cepheids have to be calibrated themselves. So we look for some Cepheids in galaxies for which we know the parallax. Okay. So we can calibrate the Cepheids, and then the Cepheids is used. There are some Cepheids which happen to which are in some galaxies where there are some supernova, and so the Cepheid can be used to calibrate the supernova themselves. So that, for the moment, the best method, as far as as I know in this. So there is 2 calibrations for the standard candles finally. Yeah.
Okay, but yeah, there is a small disagreement. I mean, it's less than 5%, so order 5%, but it's 3 sigma. It's more than 3 sigma. So it is a disagreement.
And for the moment, the measurement based on only 1 point, as you say, with gravitational wave is right in the middle of the two measurements.
Yeah, I think it's for the record. So we have to show that we have been working on this.
Okay. To measure Arch0, I also need other parameters, just like the matter density. So how the gravitational waves could handle that?
No, this is a kinematical measure. No, it's not a dynamical measure. What you are alluding to is the fact that H naught enter, so now I call it H naught, so I don't have to say Hubble elementary all the time. It enters the 0-0 Einstein equation. But this is dynamical equation. No? It relates the amount of matter to the expansion rate. Okay. This is dynamical. This is kinematical. This is just kinematics. Here you don't have to assume anything about the equation of motion. This is just kinematics. And also here it enters some second derivative of the scale factor, which is just kinematic. Of course, the dynamics of the scale factor is related to matter through general relativity, through dynamics. But this is kinematics, this is dynamics.
May you please make some comments about gravitational waves and dark matter? What are the possibilities? Gravitational waves observations.
So gravitational waves are the only thing that interact even less than dark matter. No, I don't have anything smart to say. I don't know.
Just something which has been very much discussed recently is the possibility that the black holes that have been discovered by LIGO using gravitational waves may be primordial black holes. Okay, so they are formed in the very early universe, and if this would be the case, that they would be formed before the Big Bang nucleosynthesis. Therefore, they will not be considered as made of baryons because the baryons were not yet formed, and therefore they could be part of the dark matter, these primordial black holes. So there has been a lot of discussion recently whether is it possible that the LIGO black holes discovered with gravitational waves may constitute the dark matter or may be a part of the dark matter. And as far as I know, the model, I mean that has some trouble and to explain some different. So I don't think that this model is viable for the moment. Yeah.
Yeah, let's say if it was true, it would have managed to escape many constraints, highly non-trivial. So there are many constraints there to escape. So one thing is that we know that dark matter is mostly not made of compact objects, mostly not. Because, I mean, this is from lensing observation. Because if it was compact object of roughly solar mass, half solar mass, down to 0.1 solar mass, then this compact object would deflect light. Very, very little, but piling up many observations of this would-be microlensing would have spotted them. So we know that these compact objects do not make more than 10–20% of dark matter. So they could be there. 10–20% is still a lot in the universe. But since they wouldn't be the dominant component, we need another component. We need another dominant component of dark matter. And then there is also the problem of primordial black holes. So the idea is that how do you form an object of 0.1 solar mass astrophysically? You cannot. So objects which are less than 0.1 solar masses are not compact. Now we have a lot of objects which are light in the Earth. No, it's less than 1 solar mass, but it's not compact. Basically, if the object has less mass than the solar mass, it's basically a rock. So it's not held together by gravity. it's held together by standard electromagnetic forces like that hold together anything on Earth. Okay, so if the object is too light, it cannot become compact. So we stay as the Earth, there's other planets, it will stay flat. In order for the object to become compact, it needs to have a strong, kind of strongish gravity, and that starts to happen with the sun up. You need something that has the mass of the sun or more to have a compact object. So the sun is not compact either, but it will become compact once it ends its fuel. Okay, so in order to form compact object astrophysically, you have to start with one solar mass up. The way to form compact object, sorry, yeah, I was going towards a small mass object. The LIGO black hole were 50, 60, 70 solar mass black holes that they can very well be formed astrophysically by the collapse of very massive stars, which eventually go also merger. What astrophysically you cannot form are black holes in the window of 150 solar mass. That would be problematic because yes, you do have stars, but they are unstable and they basically explode. They do not form black holes of 100 solar masses. So that would be problematic. If we see black holes of 100, 150, 200 solar masses, then it would be problematic in the standard astrophysics scenario. And then maybe formation with other exotic mechanisms like primordial black holes would gain momentum. But then how you form primordial black holes, basically you have to start with the real primordial perturbations and assume that for some region, in some region of the parameter space, they get enhanced, they get very strong and collapse. The problem is that we know the power spectrum of perturbation in the CMB window. In the CMB window, they are flat, the spectrum of perturbation, slightly reddish, so they're not completely flat. This slope is 0.96, but they are more or less flat. And above all, we know their amplitude because we know it from CMB. So these fluctuations do not form primordial black holes. So in order to form primordial black holes of the order of a solar mass, 10 solar mass, 0.1 solar masses, first we need to be very off of the CMB window because such an object would be compact, okay? So you need a fluctuation in a small region of space. And you need a huge perturbation in the primordial spectrum because you have to move from 10 to the minus 5 to 1. You need a perturbation which is of order 1 to collapse to a compact object. So you need these two problems. You need a huge features in the primordial spectrum of perturbation. So this region, now I don't remember what is this scale, but this scale in K is very large, so in size is very small. But the point is, if you want to form something at very high K, in principle, there's no reason that prevents you to do it. You just arrange a primordial spectrum, which has a huge perturbation at that high K, so at that small region. The problem is who sets it up? I mean, why such a uncommon feature? I mean, we don't have constraints, but it's very unnatural. I mean, it's not impossible, but it's very unnatural.
Is there any screening in the gravitational wave due to the other matter in the universe? There is any screening in the gravitational wave?
All right, let's start that again. The last thing I had written in the morning was an expression for the linearized Ricci tensor. Which I'm now going to rewrite in a slightly different form. So I want to swap the order of these two derivatives. So I'm going to use the Ricci tensor, sorry, the Ricci identity to swap those derivatives. I won't go through the calculation, but you can double check it if you like. When we do that, we end up with an expression that actually looks a bit more complicated, but it will be useful in a second. So we've got the same box of H alpha beta, but now when I use the Ricci identity on this, I introduce a Riemann tensor. This is a Riemann tensor of the background spacetime, contracted with H mu nu. And I have another Riemann term that's actually been contracted into a background Ricci tensor, multiplied by H. And now I have a term where these two derivatives have been reversed. So I now have grad alpha, grad mu, acting on the trace reverse of H. So here H bar is H minus 1/2 G times the trace of H. So it's called the trace reverse because if you take the trace of H bar, you get minus the trace of H. Okay, so this does look more complicated than it was up there, but it'll simplify in a second. So for the Einstein equation, what we want is not the Ricci tensor, but the Einstein tensor. So let's write the variation of the Einstein tensor. That's the variation of R alpha beta minus 1/2 G alpha beta G mu nu R mu nu. So when you write this out, you have to be careful to make sure you take the variations of the G's in addition to the variations of the R's. So we've got variation of R minus 1/2 the variation of G alpha beta G mu nu, all multiplied by the background Ricci. And then we have minus 1/2 G alpha beta G mu nu times the variation of the Ricci tensor. So now let's specialize. Everything I've said so far is very general. The background can be anything. Ultimately, we want to apply this to a Kerr background, a black hole spacetime background. So we're going to specialize to vacuum backgrounds. So in a vacuum background, the Ricci tensor of the background metric is 0. So you go over here, this term is now 0, and this term is 0. So we now have the variation of the Einstein tensor is just the trace reverse of the variation of the Ricci tensor. And a short calculation leads you to this expression. It's the box of the trace reversed perturbation minus a Riemann term contracted into trace reverse perturbation plus the second covariant derivative of h bar minus 1/2 g alpha beta, and a different second covariant derivative of h bar Now you'll notice that this is a divergence of h bar. The gradient is contracted with an index of h bar, and similarly this is another divergence of h bar. So in a second I'll show how we can set that to 0 to further simplify this. But for now this is just a general result if we have a vacuum background. Now if we want to go to second order, which we do, we need to calculate the second variation of the Einstein tensor, which will be the second variation of the Ricci tensor minus 1/2 g alpha beta g mu nu contracted in to the second variation of the Ricci tensor minus 1/2 h alpha beta g mu nu contracted into the first variation of the Ricci tensor plus 1/2 g alpha beta h mu nu contracted into, again, the first variation of the Ricci tensor. So all I'm doing here is I'm going back to this expression and taking the second variation of it, and then setting background Ricci terms to 0. So to get the value of this, we need the second variation of the Ricci tensor, and we can get that from the general expression that we had before that was exact, which was r tilde alpha beta is r alpha beta plus the things I had before, a gradient of c plus things that are square of c. So you just look for the quadratic terms in this expression. So you pick out quadratic terms that are quadratic in H. Now that's a fairly It's not too bad, but it's a little bit of a lengthy calculation, so I'm just going to give you the answer. The second variation is equal to minus 1/2 the divergence of h bar mu nu times a symmetrized derivative of h minus a different derivative of h plus 1/4 grad h grad h mu nu grad h mu nu downstairs minus 1/2 h mu nu times a second derivative symmetrized of h minus second derivative of h alpha beta minus the second derivative with the mu nu and alpha beta switched. And finally, the last term is grad nu h mu beta. And now we have an anti-symmetrized derivative of h. So this is a pretty long, ugly expression, but the key thing to note about it is just the general structure. We have things like this, which are gradient of h times gradient of h. This also has that structure, and this has the structure. And then here we have things that have the form h times second derivative of h. So knowing this general structure will be important later. And if you're really interested in second order perturbation theory, I encourage you to rederive this result. Yeah.
Why differentiate between the ATH and HTAA? By integration by parts, they are equivalent.
But what are we integrating by parts on? This is not we're not looking at an action. We're looking at a field equation.
Okay.
Yeah. Yeah. Okay, so the Einstein field equation is now given by G alpha beta of the background, which setting to 0, plus the linearized Einstein tensor constructed from H, plus the second order Einstein tensor constructed from H, plus all orders higher, is equal to 8 pi T alpha beta. Now, remember, a long time ago, I had said that H will be some power series. So now let's substitute that power series. So we have epsilon H1 alpha beta plus epsilon squared H2 plus higher order things. So when we substitute this in here, what we get is, well, we have a linear term that's linear in the first order metric perturbation. Then we have a linear term that's linear in the second order metric perturbation. Then we have this quadratic term, which is going to be just quadratic combinations of H1, because things involving H2 will be third order. And now, in place of h cubed, I write epsilon cubed. And this is equal to 8 pi t alpha beta. So if the stress energy tensor also has a power series expansion, so epsilon times T1 plus epsilon squared times T2, and so forth. Then we can just equate coefficients of powers of epsilon in this expression. And we get a sequence of equations. We have the linearized Einstein tensor constructed from H1 is equal to 8 pi T1. The linearized Einstein tensor constructed from H2 is equal to 8 pi T2 minus, going to move this quadratic piece to the right-hand side. So minus the second order Einstein tensor constructed from H1. And you can keep writing down equations to any order you like. So the key thing here is we started off with the highly nonlinear Einstein equations, and then by doing an expansion in powers of nonlinearity, this form is weakly nonlinear. All the nonlinear bits are smaller than the linear bit. That was the form that Luke showed in the first lecture this morning. And then once you actually expand things in explicit powers of a small quantity, then what we have is a sequence of linear equations. So this is a linear equation for H1. And once you know H1, you have a linear equation for H2, where H1 is now operating as a source for H2. So quadratic combinations of H1 are sourcing the second order field. So for most of these lectures, I'll be focusing on the first order equation. And I'll often write H1 just as H. So at leading order, H1 is the same as the exact H, and it can just save a bit of time writing the superscript. Okay. Now the next topic, still within just general perturbation theory, is gauge freedom in perturbation theory. And this will finally explain why I wrote everything in this fairly complicated way in terms of the trace reverse of the metric perturbation. So, gauge freedom. we can alter the form of those equations, the first order and second order Einstein equation, by utilizing the gauge freedom from GR. So note, Einstein equation is tensorial, so it's invariant under coordinate transformations for diffeomorphisms if you don't want to introduce coordinates. The approximate Einstein equations, or the perturbative Einstein equations, are invariant under infinitesimal transformations, well, coordinate transformations. So you can deal with these infinitesimal transformations, again, without introducing coordinates, but it'll be simplest to just deal with it in terms of coordinates here. So let's say you have some coordinates x alpha. I'm going to transform those coordinates to x alpha prime, which is x alpha minus epsilon times a vector c. So under that transformation, how does the exact metric transform? Well, it transforms just as it does under any coordinate transformation, but we're going to use an expansion in powers of epsilon to pick off how each piece of G tilde is affected by this transformation. So in the new coordinate system, G tilde is dx mu dx alpha prime times dx nu dx beta prime, multiplying G tilde in the old coordinates. So from this, let's rewrite this as an expression for x alpha in terms of x alpha prime. We have x alpha is x alpha prime plus epsilon c alpha plus order epsilon squared. So we have dx alpha prime acting on x alpha prime plus epsilon c alpha, and dx beta prime acting on, sorry, there should be a mu, and beta prime acting on x nu prime plus epsilon c nu, and this is multiplying, messing up my indices here. This is mu nu, and this is mu nu. And let me write the argument now in terms of the primed coordinates. So x gamma prime plus epsilon xi gamma prime. And here I'm just keeping everything to linear order in epsilon. So we have order epsilon squared corrections. So when this derivative acts on x mu prime, we just pick up Kronecker delta, and then we have the derivative of xi mu, and then similar here, we have a Kronecker delta, plus the derivative of xi nu. And let me do a Taylor series expansion of g tilde in powers of epsilon. So we have g tilde mu nu evaluated at x gamma prime plus epsilon xi gamma times derivative of g tilde mu nu, and again omitting epsilon squared terms. So this, when we multiply the two Kronecker deltas times this g tilde, we just pick up a g tilde alpha beta. And then we have a bunch of linear terms. We have xi gamma times the derivative of g tilde. Then we have these two derivatives of xi. Multiplying g tilde. So this is the alpha derivative of xi mu. Now we have the beta derivative of xi mu. Plus order epsilon squared terms. And depending how much differential geometry you studied, you'll recognize this as a Lie derivative in the direction of xi of g tilde beta. So once you're familiar with Lie derivatives, you wouldn't actually go through this calculation. You would just recognize that the expansion along the flow generated by xi is just, or this is just a linear term in that expansion. Okay, so this is still for g tilde, the total metric. Now let me split that up into a background plus a perturbation. So we have g tilde alpha beta is equal to the background plus epsilon h alpha beta. So here I'm just writing h1 as h plus order epsilon squared terms. So let's substitute this into that expression. So now we get that g tilde in the new coordinates was just g tilde, which is now the background perturbation, plus the second term, which is the Lie derivative of the background. So if we put in the h here, that's going to be order epsilon squared, so it's going to be too small to keep. plus order epsilon squared remainder. So this implies that the background just goes to the background under a gauge transformation. So in the new coordinate system, the leading order piece is still just exactly what it was before, just G. But H prime alpha beta is equal to H alpha beta, the old perturbation, plus this new piece. The Lie derivative of the background. So this is how a linearized perturbation transforms under a gauge transformation. You can extend this to any order you like. Now note that we can write this in a slightly different way. The Lie derivative of the metric is Z gamma covariant derivative acting on G alpha beta. So for a Lie derivative, you can always replace partial derivatives everywhere with covariant derivatives. And so then this term is identically 0 because it's the covariant derivative acting on the metric. And we have these two terms that are derivatives of the gauge vector xc. And for these terms, we can move the metric inside the derivative because the metric commutes with the covariant derivative. And what we get is just the gradient of z symmetrized. So it's often more useful to work with this as your gauge perturbation rather than with a Lie derivative, although sometimes it's more useful to stick with the Lie derivative. Okay. Yep. So that's just a general formula for Lie derivatives. A Lie derivative, you can always just write it with covariant derivatives here for any tensorial quantity. Yeah. Yeah. All right. So here I've been looking specifically at the metric tensor, but you can do this for any tensor. So in general, if we have a tensor, say T alpha beta with any number of indices up and down, if that is written as an expansion in powers of epsilon, then the gauge transformation of this first tensor so let me put primes there, is equal to the unprimed one plus a Lie derivative of the 0th order piece of the tensor. So you derive this exactly the way that we derived it for the metric. You just couldn't use this final simplification for a generic tensor. So, under this transformation, the linearized Einstein tensor goes to its old value plus the Lie derivative of the background Einstein tensor, but we're specializing to vacuum backgrounds, so this term is identically 0. So then we have this result, that the linearized Einstein tensor is invariant under a linear gauge transformation. So let me write an exercise to show this result directly without using this general expression in terms of Lie derivatives. So what do I mean by that? What I mean is if you calculate the linearized Einstein tensor constructed from a pure gauge perturbation, you get identically 0. So show that directly. That would be an exercise. You can either start from the expression for linearized Einstein tensor, or you can start from the expression for the linearized Ricci tensor. And note, this is in vacuum. And along the way, you should show another result, which is that the gradient or the divergence of the Riemann tensor is identically 0 in vacuum. Okay. Any questions about this? No? All right, so now we're going to use this gauge freedom to write the linearized Einstein equation in a slightly different form. A bigger piece of chalk somewhere. All right, so an example of this gauge freedom. We can impose the Lorentz gauge which is that the divergence of h bar is 0. So this is why I wrote the linearized Einstein equation in terms of things involving the divergence of h bar, because now we can set them all to 0. So in the Lorentz gauge, the linearized Einstein tensor is -1/2 times the box of h bar plus 2 times Riemann tensor contracted into h bar. And that's it. Everything else vanishes. For future use, I'm going to define this to be -1/2 E alpha beta constructed from H. So this E alpha beta is just this piece, the box of H bar plus the Riemann term. So in this gauge, let me write that as H bar there. In this gauge, the linearized Einstein equation looks like this. Just E of H bar is -16 pi T alpha beta. So this name, Lorentz gauge, is inspired by the analogous gauge condition in electromagnetism, which was just the divergence of the potential as 0. And this is also closely related to the harmonic gauge condition that Luke mentioned. Okay, now the question is, how do we know that gauge? How do we know? We can impose this. It's fairly simple to show. Let's say in the old gauge, so not the Lorentz gauge, we have H in any unspecified gauge. Then we want H nu to satisfy this condition. And H nu is H old plus the symmetrized derivative. Let me just use these parentheses to write it more quickly. I want this to satisfy this equation. Let me write that with indices in a slightly different place. So we want to set this quantity to 0. And we're going to check that we can do that. So this is equal to the divergence of this combination H minus half G mu nu H mu nu. So that's true. if and only if that's equal to 0, if and only if the divergence of h alpha beta nu minus 1/2 grad alpha g mu nu h mu nu, if and only if this is all equal to 0. And that's equal to 0 if and only if, now I'm going to substitute for h new in terms of h old and this gauge perturbation. So we get gradient, or sorry, the divergence of h old plus the divergence of this symmetrized derivative now writing out this term, we've got grad alpha h old. This is the trace of h old minus 1/2 grad alpha 2 times the divergence of mu, or sorry, of xi, all equal to 0. So this divergence of xi is coming from the fact that you're taking the trace of this symmetrized derivative. Now this is true, so this whole thing's equal to 0 if and only if the divergence of h old bar, so I'm combining this with plus grad beta, grad alpha xi beta plus box of xi alpha. So this box of xi alpha is this term here, this gradient contracted with a gradient, minus grad alpha acting on the divergence of xi is all equal to 0. Now this term here we can write in a form similar to this by again using the Ricci identity to flip these two derivatives. So this is grad alpha, grad beta, xi beta, plus the Riemann term in the Ricci identity, which is r beta gamma, beta alpha contracted into gamma. But this is 0 because we're contracting over beta here. So this is just the Ricci tensor of the background, which is 0. And then we can see that this term here is actually exactly the same as this term up here, but with a different sign. So these two terms cancel. And what we're left with is that this whole thing is equal to 0 if and only if the box of xi is minus the divergence of trace reverse perturbation in the old gauge. So I'm moving this to the right-hand side. Now this is a hyperbolic equation that we can always solve for xi. So this will have a well-posed initial value problem. So because we can always solve this equation for xi, we can always start in whatever gauge we happen to be in and then transform to a new gauge satisfying the Lorentz gauge condition. We can always find a gauge vector that will do that for us. Yep. It's right here. Oh, no, this has been combined with this to put a bar on top. Yeah. Okay, so we're almost done with this general discussion of perturbation theory and GR. Again, all this stuff with gauge transformations can be fairly straightforwardly second order, but I won't go through that here. So the last thing I want to say is something about the point particle approximation. So what we said is very generic. The only thing we specified is that the background metric is a vacuum metric. Now let's make an assumption. Let's assume at least and epsilon, the small object in the emery can be approximated by a point particle or a point mass. So what I mean by that is that I'm going to take this first order stress energy tensor to be the stress energy tensor of a point mass, which is given by this expression, x minus z of tau over square root of minus g d tau. So just as in Luke's lectures, this g is not the trace, it is the determinant of the metric. This u is the derivative of z with respect to tau, and this is a four-dimensional delta function. So to see why this is the stress energy tensor of a point particle, you can write this in local coordinates. Co-moving with gamma. So these co-moving coordinates can be t or tau xa. So one of my coordinates is proper time along the world line, and the other coordinate, or another set of three coordinates, are Cartesian-like coordinates centered on the world line. So in that case, this expression simplifies to delta alpha tau. So in these coordinates, u alpha only has a time component. And similarly, u beta just has a time component. And now this four-dimensional delta function can be written as a temporal delta function multiplying a three-dimensional delta function. And my spatial coordinates are centered on the world line. So Z A is identically 0. So this three-dimensional delta function is just delta 3 of XA. And in these locally inertial coordinates, the metric determinant is just 1. So we just have this. And now you can evaluate the integral over tau prime by using this delta function. And we've got m delta alpha tau delta beta tau delta cubed of XA. So in locally inertial coordinates that are moving along with the particle, all you have is the mass times a delta function supported at the particle's position. So this is what you'd expect for a point particle. Okay, so later in the lectures, later in the week, I'll show how you can actually derive this result rather than assume it from a more general treatment of the small object. But for now, let's